So in this section, we're going to talk about probability theory, and I will start with the definition of a probability space. So a probability space, which I here denote by W, it's a triple. So we say W is equal to a set of three elements. So we have omega, curly F, and PR. So omega is a sample space, and I'm going to explain each of these three concepts very soon. Omega is a sample space, F is the sigma algebra of events, and PR is a probability measure. So let's discuss them one by one. So what is the sample space? So sample space, which is omega, is the set of all possible samples or elementary events. So let's take an example. Consider, for instance, a die, and you throw the die once, and then we define, so here I write, we define the concept of a random variable, x. So let me explain briefly what a random variable is informally, and later I will give you a formal definition. So this concept here of a random variable, as the name says, it's a variable, and it is random. So that means x, so this is a, let me just write here, informal definition. X is a variable that can take multiple values. And take multiple values, but each of those values, you can take each of these values of a certain probability, each with a certain probability. So since we are considering a die, you know, when you throw a die, you can you look at the score on the top face, you have 6 possible values, right? So the random variable x here would be, you could take the value 1, 2, 3, 4, 5, or 6. Each of them with probability, let's say 1/6. Okay, so the same for 2, 3, and so on. So in this case, the sample space here is simply going to be the set 1, 2, 3, 4, 5, 6. Right? These are all the possible samples, also the possible things that you could see. Okay, so this is omega for a die. What happens, for instance, if we consider a coin? A coin has only a head and a tail, right? So if you throw it once, you see head or tail. So omega is simply going to be H and T, so head and tail. If you toss the coin twice, what can you see? You can see head or tail, tail head, or tail tail. Okay, so this is again omega, all the possible things you could see. And there are many examples, right, of sample spaces we'll see more later. So this is sample space, and once we have defined the sample space, we can define the sigma algebra, right? So the sigma algebra, again, remember we're looking at the definition of probability space. We've just defined omega, and F is the next thing that we want to define, which is the sigma algebra, and then we will define the probability measure. So what is this sigma algebra here? So the sigma algebra is a set of all considered events. So omega was a set of all events, and the sigma algebra is a set of all the events that you consider. So, and I'll give some examples very soon. So formally, we'll define this F here as a set of events A, and each A here is a subset of omega. However, for a sigma algebra to be valid, it has to satisfy some properties. So they have 3 different properties that it has to satisfy. First of all, the whole set, so the whole sample space omega that we've just seen here, has to be in F. The empty set also has to be in F. Right? So that means, for instance, one simple sigma algebra, F will be the set of the empty set and omega. So nothing and everything is in the sigma algebra. Then the next rule that it has to satisfy is that if a set A is in F, the complement also has to be in F. And this is, for instance, satisfied here, this example I gave you, right? So the complement of the empty set is the whole set, so it is in the set, and the complement of the whole set is the empty set, which is also in the set. Finally, if you look at all the events A in your sigma algebra, the union of these events also has to be in the sigma algebra. This is what we call closed under countable union. And the previous one, by the way, is called closed under complementation. Okay, so this is the definition of sigma algebra. Let's look at some examples. The first one is the one I already gave you. It's a trivial sigma algebra. It consists of the empty set and the set itself. So, so here it could just be any set. Like the example I gave you, I said X here was omega. So this would be what we call a trivial sigma algebra on any set X. Then what we can do, if you give me a set X, I can also take its so-called power set. The power set, it means that it's all subsets of X. So you take X, it's a set, and you take all possible subsets of this set, and this is what we call a power set. And this is essentially the largest sigma algebra you can create, right? Because you include all of it. You give me a set, and I take all of its subsets. This will be a valid sigma algebra, right? So when you take the power set, you will also include the empty set and on the whole set as well. So this is another sigma algebra. Another one is so-called Boas sigma algebra on the real line. So let me draw a simple example here. So if you take your real line, right, the one-dimensional real line R, and then you look at the so-called Boas sigma algebra on this real line. This is what we denote this BR. What is this? This is the algebra that is generated. I'm going to explain this in a minute by all the open intervals on this set. So, for instance, let's take A and B, and then we take the open interval. So we denote it in this way, right? So again, remember that open means that you're not including A and B. So usually denote it in this way, while a closed would be something with this square brackets instead. So you're looking at this open interval, then what you do to create this sigma algebra is that you take essentially the sets that can be formed from this interval here by countable unions, countable intersections, and complements. Okay, so you take your set AB, you use all these operations on this set, and then you put this in your sigma algebra. Okay, this is what we call a Boas sigma algebra. Finally, another example, let's say you give me a set X that is a discrete set. It has 3 elements in it, A, B, and C. Then what I can do is that I can create a sigma algebra. So this is just an example. For instance, I could say I put A, and I have B and C. And then again, I have to also add the empty set and the whole set. Right, and you can see this is a valid sigma algebra because the complement of A is BC, so it's in the set. And the complement of BC is A, and that's also in the set. All right, so these are some examples of sigma algebra. And now let's move on to the last element in our triple, right? So we've covered omega, sigma algebra F, and next we want to cover the probability measure. So this probability measure here, which we again denote by PR, it's a function. And this is a function from F, so from the sigma algebra, to the set 0, 1. Right, so, and this is what we call a probability measure if it satisfies 3 properties. First of all, it has to be non-negative, which makes sense, right? It's a probability. You cannot assign a negative probability to a set A, right? So you take a set A in your sigma algebra, this probability has to be greater or equal than to 0. Next is that if you measure the probability of the whole set, it has to be 1. Okay, so there's a normalization. The probability of everything has to be equal to 1. And finally, there's a so-called sigma additivity property, which means that if you give me a set of events, so an here, so take, for example, n equal 2, so you have a1 and a2, then and those sets here are disjoint, so that means the intersection is empty if I is different from j here. Then the probability of the union has to be the sum of the probabilities. Right? So if we just take, for instance, n equal to 2, that would say that the probability of A1 plus A2, and remember those are disjoint events, right? Then this probability is simply equal to the probability of A1 plus the probability of A2, right? So because they're disjoint, so there's no joint distribution between them. So simply we get this sum here. Let me give you an illustration here that I took from Wikipedia to illustrate, again, this concept of probability space and probability measure. So consider, for instance, the case where our sample space, omega, is the set of 1, 2, and 3. So as shown here on this picture, we will say that the probability of 1 is 1 quarter, probability of 2 is 1 quarter, and the probability of 3 is 1/2. Right, so represented here by this area here. So how can I understand what this probability measure is? So here, let's look at a sigma algebra. Let me write it with a small sigma. So this is our sigma algebra. What is in the sigma algebra? Where we said we have to have the empty set, we have to have the whole set, and then we'll have 1, 2, and 3. So we have 1, 2, and 3. And then we have also all the pairs. So 1, 2, 1, 3, 2, 3. And now we understand what probability, what is the probability of each of those sets. So the probability of the empty set is 0. So you see here, P here is a function that would map this empty set to 0, right? So as we said before, let me write as PR here. PR is a function from F to 0, 1. And what we are saying is that PR of the empty set, let me do it this way, is simply 0. What did we say? We also said that if I were to take the whole set, omega, the probability is 1. So you can see here the probability of the whole set, omega, maps to 1. Okay, so the empty set maps to 0. The whole set, omega, maps to 1. And then the rest, well, it's given here on this picture, right? So again, we said the probability of 1 is 1 quarter. The probability of 2 here is also 1 quarter. The probability of 3 is 1/2. And how do you get the probability of 1, 2, 1, 3, and 2, 3? You can use the countable the additivity property that we discussed before, right? So what we said is that 1, 2, the probability is going to be the probability of 1, which is 1 quarter, and the probability of 2, which is 1 quarter, so that's 1/2. For the probability of 1, 3, it's going to be the probability of 1, which is 1 quarter, plus the probability of 3, which is 1/2, which gives us 3/4. Okay, so you can think of essentially this probability measure as taking all your sigma algebra, all the events that you consider, and then it gives you a map on this real line here between 0 and 1, and it tells you what is the probability of each of those events. All right, so now that we've seen this concept of probability space, let me define this concept of random variable, which I've introduced before, but in some informal way. So what did I say before in some informal way? I said the random variable, it's a variable, but it doesn't take just one value. It takes a range of possible values. And each of them with certain probability, right? So I told you, for instance, X could be 1, 2, and 3, right? With probability 1/2, 1/2, no, sorry, 1 quarter, 1 quarter, and 1/2. All right, so this is what random variable is. I also here write a formal definition if you prefer. So you could say that given our probability space, which we have just defined, the random variable is a function from omega to what we call a measurable space. So this is a bit technical. We don't necessarily need to understand this in all the details, but a measurable space, it's a set that we can measure. So that means it can be equipped with this probability measure. That's what it means. Okay, so this is the definition of a random variable. And let me give you some examples. I mean, we've already seen some, but let's look at some more complex examples. Let's say that you throw two dice, then what is your sigma algebra? You can actually here take it to be this set 1, 2, 3, 4, 5, 6 squared. Okay, so because you have two dice. You could say that the sigma algebra is a power set, but we said that's one way that you can take your sigma algebra. So again, it's a set of all subsets. So you have 1, 1, 1, 2, and so on. And then you could say, okay, what I'm going to measure, I'm going to define a random variable x, and I would say it's the sum of the numbers on each die. So here I would just say this random variable essentially again, it's a function, right, from omega, which here has just two elements in it, omega 1, omega 2, and the random variable itself would just be omega 1 plus omega 2. So this is one example of a random variable. Another example, so we do the same, we take two dice, and then we again have the same sample space, but let's say that now for the sigma algebra, we just take the trivial sigma algebra, so empty set or the whole set. Then here you have to be careful because x, as defined in A, so the thing we've just defined here, the sum, is not a random variable. And the reason is that if you look at, this is a little bit technical, but if you look at the inverse of, for instance, 2, you can see this will be 1, 1. But this is not in our sigma algebra. And this is a condition that we need formally for random variables, is that they have to actually satisfy that the inverse, so if you take x minus 1 over omega, right, that this has to be in the sigma algebra, and it is not in this case. This is a little bit technical. It's okay if you don't necessarily understand the technicality here of this example. It's just to tell you that you have to be a little bit careful. But in all the examples that we will see, usually, I will define random variables and they will be valid. Okay, let me explain a little bit more so the subtleties between discrete and continuous probability space. So far, I did not actually differentiate between these two cases. And these are things that you've already seen. So we're going to put this into, again, the language that I've just used so far. So let's look at, for instance, here on the left, a discrete probability space, and on the right, a continuous probability space. So for instance, in this case, in the discrete case, we have, again, a discrete probability measure, right? So think of the example of the die, right? So we said we look at a random variable x that can take 6 possible values. So here we have 1, 2, 3, 4, 5, and 6. And then here you have the probability mass of each of the possible values. Okay, so here 1 takes this value and so on. Let's say 2, you cannot get it. So let's say this die is biased, that you can never get a 2 on it. And so this is a probability. This is actually what's the so-called probability mass function. Right? So it tells you what is the probability of x to be equal to 1, the probability of x to be equal to 0, to 2, and so on. In this case, in the discrete case, this probability of x, of the random variable x to be equal to small x, is defined by a function f of x. Let's now look at the case on the right-hand side, where now you have something continuous. So, for instance, just think of a probability distribution that is the Gaussian, right? So let's just say that you have the probability of a random variable x is defined according to a Gaussian distribution, which you typically denote here by this curly n. And as you might remember, right, so here we usually write the mean. So let's say it has a mean 0 and it has some variance sigma squared. So on this drawing here, this is let me put this here at the bottom. So we have this axis here, this Gaussian here centered at 0, let's say, and so this is just an illustration of a Gaussian for a random variable x that has a Gaussian distribution. So in this case, instead of talking about a probability mass function, we talk about a probability density function. And the way that we typically get so here there's a typo, what I want to write is this. The way that we typically measure the probability density function is so by integrating f of x. I'm going to elaborate on this in the next slide. So for now, I just want to give you a rough understanding of what we're going to discuss. So let's dig a little bit more into the subtleties of discrete and continuous. So let's say now we want to define a discrete probability space. So remember, again, a probability space here was defined as a triple. We need omega, we need F, the sigma algebra, and we need a probability measure. So that's what I wrote here. This is a definition. And this probability measure here, PR, in the discrete case, as I wrote in the previous slide, it's going to be a probability mass function. Probability mass function, which we write as PMF. What is the sample space? So the sample space is going to be something countable and finite, right? An example of the die with 6 different faces. We've seen this before. Sigma algebra, we've seen examples before. So for instance, you could take the power set. And then, as I mentioned before, this probability measure has to satisfy some properties, right? So we said it had to be non-zero, non-negative, and it has to be normalized. So it has to have this normalization properties. So this is how you define the discrete probability space. And now let's look at the continuous probability space. So what is going to change here? So we still have, our triple. So we still just say W is omega F and PR. The probability, this probability measure now is going to be something that we call a probability density function, as I've mentioned before. So we call this a PDF. And again, it has to satisfy the same properties. So it has to be non-negative, and it has to also be normalized. And I'll give you again an example in a minute. So, well, let's look at it here actually. So let's look again at the example of the Gaussian. So here I've drawn a Gaussian distribution centered at 5, right? And how do we actually get, let's say, the probability of, so we have a random variable x, let me highlight it. And let's say we want to get the probability of x to lie between a and b. So let me highlight these 2 intervals, a and b. Let's say here it's 2 and 8. So how would you get this? So if you want to know that this random variable is between a and b, right? So intuitively, what you will do is you will integrate this. So I'm not doing this very well here. Let me show you this better. But you will integrate essentially all of this region here under the curve. Okay, so this whole thing here. Okay, this is how you would integrate this whole thing here. And this is what I've written here. You see, like you're integrating between a and b. So you have this integral here between a of b of this f of x. And f of x is a so-called density. So it tells you essentially the value of small x. Okay. And to get the whole probability of this interval, you have to integrate this whole thing here. Okay, this is so-called probability density function. So here I put also another definition, which you might have heard of before, the so-called cumulative distribution. Would not necessarily need this in the class. I mean, it's something maybe to be aware of, is that the difference between the PDF and the cumulative distribution function is that here you're integrating everything between -infinity and x. So usually you say the cumulative distribution of x is essentially integrating this density function again between -infinity and x. Okay. All right. So these are something that we won't really need. I just put it here in case you do further reading and you encounter this definition so that you're not confused. This is slightly different. The cumulative distribution function is slightly different from the PDF. So in the discrete case, we again get the so-called PMF, right? The probability mass function. And now what is going to change is that while before we had this sort of integration when we wanted to measure the probability of a random variable x to be in some interval, Now it's discrete. So we really measure the probability of X to take a certain value, discrete value, right? So in the example of the die, again, what we said, what is the probability of X to be equal to 1 or 2 up to 6? Right, so I can ask, what is the probability that when I throw a die and I look at the top face, its value is 1. And then we know this is 1/6, we said. Okay. And now, so here also one small thing is that if you're looking at the probability of a set, right? So instead, let's say you get a probability of a set instead of a singleton, then you have to sum over all the elements omega in the set. Okay. All right. So the integral, if you want, while we had an integral before for the continuous case, this integral now becomes a sum. Finally, this will be the last concept for this section. So let's discuss what is an expectation. I've already alluded to this before, but let me now define this formally. So an expectation is something we're going to denote here with this E. We take the expectation of run-off variable X. And what we do is that we'll integrate on the whole domain. And we're going to integrate the value of X weighted by the density. Okay, so let me rewrite this here. This is again the density. Okay, so we do X times f of X. So for instance, if you were looking at integrating or calculating the expectation of the Gaussian, let me again here draw this. So let's say we take our Gaussian, let's say it's centered here, and then we have this profile here, which is not very good, but okay, I think you get the point. And now I would like to know where is the expectation. So the expectation here is at this place, that is at where it's centered, at the mean. So the expectation in this case is the mean here. So this is what the expectation is in the continuous case. In the discrete case, simply, as I already mentioned before, this integral here will be replaced by a sum. You have to sum over all possible events, right? So in discrete case, you have a list of possible outcomes. Your run-off variable can take, let's say, xk possible outcomes. Again, in the die, we have 6 possible outcomes, and then we will simply sum over all these possible outcomes. So let's, for instance, look at again, our example of X being the die. So 1, 2, and so on, 6 with each with probability 1, 6. And let's say I'm asking you what is the expectation of X. So what do you have to do here? You have to sum over I from 1 to 6. We have 6 possible values times xi. So in this case, let's say xi is just I itself. And then pi is right. So this probability pi, we said is 1/6. Okay, so simply here you can see this is 1/6 times the sum here. Okay, and so this you can calculate. All right, so this is, for instance, how you could calculate the expectation of your random variable. And I will tell you, an expectation, what if I, what am I supposed to get if I were to essentially repeat this experiment, I throw the die, what value do I get on average, essentially, right? So if you throw it like, 10,000 times, you calculate the expectation and you will see what value you're supposed to get.